Subatomic particles. Proton, neutron, electron. What's the charge of a proton? +1. Charge of a neutron. 0 or neutral. Charge of an electron. -1. Proton and electron are equal in magnitude, opposite in charge. Mass. Mass of a proton, 1 AMU. Mass of a neutron, the same, 1 AMU. Mass of an electron is about 0. Location. Protons and neutrons are both in the nucleus.
What sign is that? Cloud.
Electrons are in the electron cloud or in orbitals. Okay? Let's see. What else from Unit 1? Atomic mass is the weighted average of the naturally occurring isotopes. That's one where you have to do that crazy math. Let's see. You need to know the gold foil experiment. There were 2 conclusions. 1, atom is mostly empty space. Why? Because the alpha particles passed through. 2, the atom has a small, dense, positive nucleus. Why? Because some of the alpha particles were deflected. Atomic number tells you the number of protons, and it IDs the element. Mass number is equal to the number of protons plus the number of neutrons. So the number of neutrons is equal to the mass minus the atomic number.
I feel like I'm in this room already.
Remember, if you miss something, this video will be online. Going fast because tick-tock, tick-tock, tick-tock. By the way, and this will be in the video too, in college, they go faster. Just get ready. All right. Let's see. Okay, Unit 2, periodic table. Below the stairs. Above the stairs. On the stairs. Except aluminum is a metal. Group 1, alkali metals. Group 2, alkaline earth metals. Group 3 through 12, transition metals. They have multiple oxidation states and colored ions in solution. Group 17 are halogens. Group 18, noble gases, aka inert gases. They are stable or have a full valence shell. The last number of the electron configuration tells you how many valence electrons. Additionally, the group number does. Group 1 has 1 valence electron. Group 2 has 2. Group 13, well, it can't have 13, so it has 3 valence electrons. Group 14 has 4, etc., etc. Liquids. Mercury and bromine. Gases. Hydrogen, nitrogen, oxygen, fluorine, and chlorine, and group 18. Solid, the rest are solid. Now, here I kind of cheated. I really should write these as their diatomics because they are part of Brinkelhoffs. Remember, Brinkelhoffs are not diatomic when they are in a compound. They are only diatomic by themselves. All right, trends. Going across a period. Things that increase ionization energy and electronegativity. Remember, on the regions, write the word out. Things that decrease atomic radius and metallic character. Why? Because as you go across, increased nuclear charge. Going down a group, everything is the opposite. So ionization energy and electronegativity both decrease. Atomic radius and metallic character both increase. Reaction types. All right, we're going to start with the early ones that we learned in Unit 3. These are basic chemical reactions. Synthesis. Something like this. Two things on the left, one on the right. Decomposition. Something like this. I'm not going to balance it. One thing on the left, two on the right. It's showing this breaks down into those. Single replacement. Not balanced. Element in a compound, zinc kicks out the hydrogen. Why does zinc kick out the hydrogen? Because zinc is higher on the activity series. It's more easily oxidized. It's more active than hydrogen, so it kicks it out. Double replacement. I did the demonstration of potassium iodide with the lead nitrate. We got potassium nitrate. That was aqueous, so we didn't see anything. And lead iodide, which was that bright yellow solid. That's why it turned bright yellow instantly. At that time, we talked about one organic reaction, but we didn't label it as such. Combustion. A hydrocarbon burns in the presence of oxygen to make CO2 and H2O, also unbalanced. When we name things, non-metal, we use prefixes. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona. I'm not leaving off the us because duh. And deca. Metal, non-metal, no prefixes. Okay? For all, the more electronegative ends in ide. Hydrogen becomes hydride. Fluorine becomes fluoride. Oxygen becomes oxide. When we see something like copper 2 chloride, what does the 2 mean? It's the oxidation state of the copper. So it's Cu plus 2. Cl minus 1. So we get CuCl2. You got to remember that this is the oxidation state of the metal. All right. Bonding, Unit 4. Type, ionic, covalent, metallic. Yep, these are all bonding. The types of bond. Ionic, between metal, non-metal. Covalent, between non-metal, non-metal. Metallic, just metal. Electrons, ionic, transferred. Covalent, shared. Metallic, mobile. Ionic substances, salts, tend to have very high melting point, boiling point. They conduct electricity only as a liquid or aqueous, not as a solid. Covalent tends to have low melting point, boiling point. They do not conduct electricity. Metallic tends to have a moderately high melting point, boiling point, and they always conduct electricity. AKA for covalent, molecular. If we have something with a polyatomic ion, polyatomic ion in a compound, it has both ionic and covalent bonds. All right, intermolecular forces. Strong, these are IMFs. To weak, strongest intermolecular forces is hydrogen, not a real bonding. Remember, it's not a real bond. To have hydrogen bonding, you need hydrogen with either nitrogen, oxygen, or fluorine, and it must be polar. Next, dipole-dipole. Simply needs to be polar. Finally, we have London dispersion forces. That's in things that are non-polar. Larger are stronger, smaller are weaker. Okay, larger molecules have stronger dispersion forces, smaller molecules have weaker dispersion forces. Okay? Next thing, we gotta know cold. Is heating cooling curve. This line should be a lot longer if it was water. Get a little more space here. All right, a little better. Solid, liquid, gas. Phase change from a solid to liquid, melting. Phase change from a liquid to a gas, vaporization. Evaporation or boiling are usually acceptable, but vaporization is correct. Solid directly to a gas, sublimation. All of these going up, endothermic. So going down would be exothermic. All right. Gas directly to solid is deposition. Gas to liquid, condensation. Liquid to solid, freezing. All of these changes, all of these phase changes are physical changes. Don't mix them up. Anytime it is sloping up, while it is a solid or liquid or gas, kinetic energy is increasing. Anytime it's sloping down, when it's a solid, liquid, or gas, kinetic energy is decreasing. During a phase change on the up curve, potential energy is increasing. Phase change on the down, the cooling curve. Potential energy is decreasing. While it's heating or cooling, any of the ones that slope up or down, the formula you use is Q equals mc delta T. We almost never see it. The C on the reference table is for water, that 4.18. If it's ice or steam, it'll be a different number and they'll give it to you. So 4.18 is here, different there and there. Melting, freezing. Q equals MHF. The reason why I stress vaporization, Q equals MHV. This line should be for water 7 times longer than this line because the heat of vaporization is about 7 times longer than the heat of fusion. When you dissolve something in water, it raises the boiling point and lowers the freezing point, dependent on the number of particles. Okay? So increased concentration raises the BP more and depresses the FP more. Sugar. Put it in water, it doesn't dissociate. You get 1 particle. NaCl, you get 2. CaCl2, you get 3. AlCl, so it's, no, Al, say AlO, Al2O3, you get 5. This pushes it up the most. This pushes it up the least. More particles affects the freezing point and boiling point more. Exo, endo. For both, going from the potential energy of the reactants to the top is the activation energy. This is the potential energy of the products. The difference between the potential energy of the products minus the potential energy of the reactants is delta H, the heat of reaction. They are listed on table I. Table I tells you delta H is the heat of reaction. And it tells you that for exo, delta H is negative. For endo, delta H is positive. You have to know that for a reaction to be at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. And the concentrations stay constant of everything, of all the reactants and products. Additionally, it has to be in a closed system, so nothing can enter, nothing can leave. All organic compounds contain carbon. That is always the answer for the element present in all organic compounds. Most have hydrogen. A lot have oxygen. Those are never the answer. It's always carbon. Carbon bonds to itself in rings, chains, and networks. 20 years from now, somebody's listening to that on the video. All right. Carbon, always for bonds. Hydrocarbon, saturated all single carbon-carbon bonds, unsaturated at least one multiple carbon-carbon bond. Specify the carbon-carbon. COH, alcohol. CHO, aldehyde. COOH, organic acid. We're good. Organic reactions. Addition. Addition, you're going to have a saturated hydrocarbon plus something. Oh, sorry. Addition, you have an unsaturated hydrocarbon plus something. And it adds, it breaks this bond and adds it in, and you get single bonded carbons with that something. Substitution. That starts with a saturated hydrocarbon. Something goes in, something goes out. Bromine kicked out a carbon. Fermentation. Sugar. In the presence of an enzyme, a catalyst provided by yeast, makes carbon dioxide and alcohol. Ethanol, usually. In the space I have here, saponification, making soap. What's left? Polymerization. Lots of monomers make one polymer. There's addition and dehydration. If it's dehydration, there'll be plus H2O and a certain number of them. Esterification. An alcohol plus an organic acid makes an ester and water. And we already talked about combustion. Oil rig. Oxidation is losing. Reduction is gaining. Don't forget, homework 8.1 has the rules for assigning oxidation states. Red cat gets fat and ox. Reduction is at the cathode. That's going to grow. Oxidation is at the anode. Because atoms are oxidized to aqueous ions. Voltaic cell is a battery. A spontaneous redox reaction. Higher on table J, the activity series, replaces lower. Salt bridge, flow of ions. Electrolytic cell needs a battery. It is because it's non-spontaneous. It doesn't have a salt bridge. Voltaic cell had 2 half cells. Electrolytic cell has 1. The electrons flow out the negative terminal of the battery. Thank you. That's going to be on there forever now. Arrhenius acid produces hydronium or hydrogen ion as the only positive ion in aqueous solution.
Did I say A produces?
Arrhenius acid produces hydronium or hydrogen ion as the only positive ion in an aqueous solution. I'll put an AQ here.
What are you drinking?
An Arrhenius base produces hydroxide. Don't mess up the names, they're on table E.
So is that a hydrogen ion versus positive?
Hydrogen ion is always positive, H+. A hydrogen that was negative ion is called hydride. Remember, negative ion is always going to end in "ide." So base produces hydroxide ions as the only negative ion in solution. The other theory, Bronsted-Lowry, acid is a proton, that's a proton, donor. A base is a proton acceptor. Neutralization. Neutralization is the reaction. Titration is the lab procedure. Acid plus base makes salt and water. For example, HCl plus NaOH yields NaCl plus HOH, or you can write it H2O. All nuclear reactions are transmutation, where something changes into another element. Natural is going to be decay. When we look at something natural, there will be one thing on the left and two on the right. It'll be alpha decay, beta decay, positron decay. Then you have artificial. There's two or more on the left, or there could be two. Okay? And two or more on the right are artificial. Fission. Something big plus a bullet becoming two smaller things and usually more bullets. This is usually going to be some sort of uranium. Fusion is almost always going to look like this. Hydrogen 3, tritium, plus hydrogen 2, deuterium. Going to make helium 4-2 plus a neutron. All right. All of that you should be able to write out quickly.